finish the notes. So we're going to do the trapezoidal trough problem and then the shadow problems as well. Okay? So the first one says the cross-section of a 5-meter trough is an isosceles trapezoid with a 2-meter lower base. So this distance from here to here is 2. A 3-meter upper base. So that's the upper base of the trough, but not necessarily like the upper base of the water, right? In an altitude of 2 meters. So this distance up and down is 2 meters. And it says the cross-section of a 5-meter trough, so the 5 meters is going to be the length here. So 5. So we have a trapezoidal trough container, but we also have a trapezoidal solid that's formed with the water. It's not really solid if it's water, but you know what I'm saying. Right, so the volume of the water is a trapezoid, has a trapezoid for its bases. Okay, so this shape is also a trapezoid there, and it goes out. Okay, so we need to come up with a volume of the water in order to do this problem. So our volume has, there's usually 2 equations for volume. One of them is 1/3 area of the base times the height, and one of them is just the area of the base times the height. Do you guys remember this from geometry? No, not at all. Maybe I should print some of these formulas. So this is going to be the area of the base times the height because there's 2 bases, and those bases are trapezoids. So a trapezoid has a certain area. Do you guys know the area of a trapezoid? Did I show you this the other day? No, I think I showed the other class. So a trapezoid involves something called a mid-segment. And a mid-segment is the average of your 2 bases. So what's the average of our 2 bases? I would do B1 plus B2 divided by 2 to find the average of the 2 bases. Here's how you derive the trapezoid formula. It's so easy, but like no geometry teachers do this. It's like the easiest way. You just cut it off. So you cut this part off and you move it right here. And then same idea here. So where the mid-segment joins, you cut off the triangle and you move it down here. And you get a rectangle, which has an area, mid-segment times the height, right? So the area of a trapezoid is 1/2 B1 plus B2 divided by h. So we write 1/2 h times B1 plus B2. But then we have this other h. And that other h is not, that's like the distance between the 2 bases. So instead of calling it h, I'm going to call it L. And that's going to stand for like the length separating the 2 bases. Does that make sense? Sorry, I ate a Snickers and now I'm choking on a peanut. No problem. All right. So this is going to be my volume. So remember how I told you about that lady at that conference who was like, I never let my students plug in constants. I was just like, okay, well, you're not teaching them how to do calculus then, because like this problem without plugging in the constants, look how hard this would be. You have 4 variables. You'd have to do like product rule like 3 times. Yeah. What do you think?
I have a question. So, what's that? Sorry. Okay, so you're solving it right now where you're doing the base as the trapezoid.
Uh-huh.
And then the height as the...
Yeah, you cannot do it where the bases are the rectangles.
Why not?
Because in order to use this formula, area of the base times the height, you need the bases to be parallel and the same shape.
Yeah,
Like the same size, I guess I should say.
So I'm saying,
So
obviously this would be a much longer way, but theoretically, could you just like, because I kind of didn't know we were supposed to do this one on the homework, so I did it on the homework.
the answer is no, Ari. You cannot do it that way. No, there's no way.
If you chopped it and added the 3 volumes, so you have a triangle.
I guess, yeah, if you're cutting it this way.
Yeah.
That sounds overly complicated in an already complicated question. All right, so we're gonna get there. We actually are doing something kind of similar to that, all right? But can I at least do the problem and then you can ask me questions? It's gonna be the longest problem ever if you keep asking questions every 2 seconds. All right, so here's our volume equation. So as I was saying, you don't want to take the derivative from here. You want to plug in anything that's constant. 2 of these numbers are constant. What 2 numbers? This base, because no matter what, as that water's draining, unless it's empty, right, the base of that water is going to be 2. And then this right here is constant. But the water started out, like if it was totally full, it started out with a top base of 3, but it's draining, so that base is getting smaller. Do you guys see, like this will go smaller, 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 smaller. All right, so that one changes, and as does the height. So it started out with 2, but then it gets smaller, smaller, smaller for the height. So those two are not constant. So we're going to plug in. I'll call it B2. So we're going to plug in B2 as 2, and we're going to plug in L as 5. But it's still kind of complicated. We got B1 and H. So this water problem should kind of remind you of the ones we did that were inverted cones. And the thing that's nice about inverted cones is that we can set up, oops, I deleted a lot of that. We can set up similar triangles. So let's say we had like 3 and 10, and then we had the radius and the height of the water. We would do like 3 over 10 equals R over H, right? Or 3 over R equals 10 over H. Okay, and we can kind of do this here. But why is, if I have a trapezoid and I have its water, that's a terrible trapezoid. Why is this trapezoid right here of the water, why can it not possibly be similar to this trapezoid here? Yeah. Yeah, totally. Did you guys see that? So in order for trapezoids to be similar, they need to be exactly the same shape, and all of their sides need to be in the same proportion. So if this was in the ratio of like 2 to 1, this one would be like 10, and this one would be 5, right? Look at the problem here. When you have this blue trapezoid inside the red trapezoid, those bases are the same. Those can't possibly be similar trapezoids, right? We have similar, like we can use similar trapezoids in general, but this is not a similar trapezoid situation. Yeah. Ah, yes. So that's why I said, Ari, it is kind of similar to what you were talking about.
Yeah, you cut it,
we'll see.
You cut it into a
So we're going to cut it right here.
Yeah.
So here's what we're going to have. And this is where you might need more paper because you might want to see this a little bit bigger. We have this trapezoid that's created, and we're cutting off these edges. And we have a trapezoid inside of it that is a trapezoid of water. Okay, the top was 3. The bottom was a constant 2. B1 is the distance, like that's what I'm representing for the base of the water, so going all the way over here. Right, do you guys see it? H is the height of the water, so this is H. We have similar, not trapezoids, but similar triangles. Do you see the similar triangles? Okay, so our similar triangles, let me use another color, are right here. Whoops, I picked green and it didn't do green. It's right here. Did you guys see? Okay. Can you figure out what this distance is right there? Yeah, 0.5. All right, so we have 0.5 to, I'll call it x. So 0.5 over x is the same as this to this. So what was the total height? 2. So 2 over h. And you can cross multiply. We get 0.5h equals 2x, which means h is equal to, if I multiply by 2 on both sides, 4x. So we can use that. Okay, so if I wanted to get everything in terms of one variable, I could. So I can, like, look at my equation right now for volume. I have h and I have b1. I can get it all in terms of h or all in terms of b1. It doesn't matter which one you do. So looking at b1, write an equation for b1 using x's. b1 is equal to what? So an x is here and x is here. Yeah, 2 plus 2x. This distance is 2. Do you guys agree that it's 2? That was 2, this is 2, right? Do you guys see it? So we had 2 here and we had 2 here. So b1 is equal to 2 plus 2x. So I can replace my b1s with x's, or I can replace my h's with x's. Let's just do that. Let's make everything in terms of x. So I'm going to take this volume equation, and I'm going to say, well, it was really 1/2 h. Well, h is 4x, and it's b1, which is 2 plus 2x plus 2 times the 5. Now everything's in terms of x. Phil, you with me? All right, so we're just going to simplify this. So I have 1/2 times 4x times, I'll do the 5 first. So that's 10x times 4 plus 2x, which ends up being like 40x plus 20x squared. Isn't that so much easier? We went from an equation that had 4 variables, h, b1, b2, and l, down to one that just has, well, 5 variables if we count v, right? So now we have v and x. Can you take the derivative of that? All right, do that.
But, are we sure this is what?
Okay, so the question is, what do we want to find in the problem? We want to find how fast the water level is rising. So if you notice that, you could replace your x's with h's now. You could be like, oh, well, I didn't want x, I wanted h. So h is the same as 4x, so x would be replaced with h over 4, right? So you could do that. But remember, this is related rates. So with related rates, if you solve for the wrong thing, it's cool. Like, I'm just going to go ahead and solve it like it is for x. And then I'm going to relate my two rates to each other using this equation, right? So that's okay. We can do that. So let's say we solve for dx over dt. So it said the water level, what did it say, was rising at 1 cubic meter per something minute? Yeah. So dv over dt is 1. Dx over dt was what we're trying to find. X we don't know. But we're saying how fast is the water level rising when the...
Why is it 40?
The derivative. The derivative of...
Why is it 40x plus 20x squared?
So like I multiplied the 10x in. So I did this times this. I think I'm good. All right, so that's what I had in the first period class too. All right, so we want to know, it says water is running into the trough at a rate of 1 cubic meter per minute. How fast is the water level rising when the water is 1 meter deep? So we want that 1 meter deep. So that is h equals 1, right? So when h is equal to 1, we want to find dh over dt. So if h is 1, x is 1/4, so plug the 1/4 in. See how we're relating our rates, relating things together. So we get 40 plus 10, and then they both have dx over dt, so that's 50 dx over dt equals 1. So we have dx over dt is equal to 1 over 50. Okay, but again, we wanted dh over dt. And that happens all the time as people are solving related rates. You will probably do this on the AP test, and you'll probably panic and be like, oh my god, why did I do that? I meant to solve for dr over dt, and I found dh over dt, or whatever, okay? So in this case, we found dx over dt. Don't erase your work. Like, all that work is good. So now you go back to any equation that relates what you want. So we want dh over dt, and we have dx over dt. So remember, x was equal to, where was it? Or h is equal to 4x, right? So 4x equals h. So that means 4 dx over dt has to equal dh over dt. They're related in that rate. Like those two rates are related to each other, in that ratio. So that means I have 4 times 1 over 50 equals dh over dt, which would be, 2 over 25. Or 0.08 if you want a decimal. And that's in meters per minute. That's our answer. Okay, so don't freak out if you solve for the wrong thing. You can always get it. Okay, does this make sense? It's a hard one. It's a lot for the very first problem. I probably should have done the shadow one first. All right, so let's try the shadow one. Okay, so the shadow problems are classic related rates problems that can be found in every single textbook. So these are in every single Calc 1 course. Okay. They usually don't put them on the free response, but they'll put them on the multiple choice on the AP exam. Okay, so Grace is 5 feet 6 inches tall, and she walks at a rate of 4 feet per second away from a light that is 15 feet above the ground. So here's our light, and then it's shining down, and Grace is standing, and she has a certain shadow that's created. So the distance there to there. Okay. and she's
So we're
walking
assuming
away.
that the-
Mhm.
That's how the shadow.
I don't know how the shadow would not be like that, but yeah, how's the shadow?
If you have enough mass, it'll
Yeah.
bend the light around you.
Okay. All right, so to be very physically. All right, so if we have this distance here, I'm going to call S for shadow. And this distance here, I'm going to call X. That's the distance that she is from the light. Are either of those constant? No. Okay, now let's imagine the situation. If I'm standing directly underneath the light, is my shadow big or is it small? It's small. Have you guys ever seen? I mean, think about the sun when it's directly overhead. Your shadow is like non-existent, right? You look down and you're like, oh, I don't have a shadow, right? But if the sun is way over there, like my kids love that when it's like the sun is setting. They're like, look how big my shadow is. And their shadow's like 20 feet long, right? They love that. Okay, do you guys remember doing this as a kid? All right, so you still do that. You're like, look how big my shadow. Let's take a picture of my shadow. All right, so anyway, so the closer you are to the light, that means the light was going straight down. And so if you're right there, your shadow is tiny, right? And then the further away you are, the longer your shadow is. Does that make sense? Okay, so that's the situation we have going on. So X changes and S changes. She's walking away. So dx over dt is how quickly she's walking away. And we said she was walking away at what, like 4 feet per second or something? All right, so that's going to be 4. All right, we want to find how quickly the shadow is changing. Okay, and as she's walking away, the shadow is getting bigger and bigger and bigger, right? Like we just talked about. So this, again, is similar triangles. So we have a big triangle, and we have a small triangle. The whole distance here is x plus s. So our similar triangles are going to be 15 over her height, which was what? Yeah, 5.5, right? 5 feet 6 inches. So 5.5 equals, I did this backwards than what I usually do. That's fine. So 15 over 5.5 equals total x plus s over s, right?
Could you also do like 15 over?
Yeah, that's what I usually do. I usually 15 over x plus s equals 5.5 over s. Yeah, you could do either way. It doesn't matter. Okay, so when you cross multiply, don't you see you get the same thing? So let's cross multiply. Because we don't want to take the derivative as is, because then we have to do the quotient rule, and that's no fun. So really, we just need any equation that relates our x and s. So could we continue to simplify? Sure. So 15s equals 5.5x plus 5.5s. Subtract the 5.5 over, we get 9.5s equals 5.5x. You could even like divide by 5.5 or clear the decimals by multiplying by 10, whatever you want to do. So we're good to go here. Okay, that's fine. Very, very easy to take the derivative of now, right? So we're going to do 9.5 ds over dt equals 5.5 dx over dt. And we plug in. So we have dx over dt is 4, right? So we plug 4 in. It's a decimal point, not a multiplication. And then I divide by 9.5 to get ds over dt. So 5.5 times 4 divided by 9.5. So I got 2.316. And this is in feet per second. Is that right?
Yes.
Units, feet per second. Okay. That's how quickly her shadow changes. So as she's moving away from the light, her shadow is getting bigger. That's why it's positive. Makes sense, right? We got it? All right, now part B. Look at part B. It says, how quickly does the tip of her shadow change? And that's when people always look at me. So Alexa's looking at me right now, and she's like, how is that any different? Right? That's totally what you're thinking, isn't it? That is exactly the same, Mrs. Cox, right? It's not. Okay, so as she's moving, the shadow is getting bigger. And the shadow is getting bigger at that rate. But she's also moving. So the end of her shadow is getting further out because she's also moving. So I know this is a hard concept to understand. It's weird. So like the shadow gets bigger, That's what we just found. So the further she gets out, right, we said, oh, if I'm really far away, the shadow's really long, right? We talked about that. But this distance is also changing. She's getting bigger. Like, she's not getting bigger. That would be weird. She's getting further from the light. So we need to consider that she's walking and her shadow's getting bigger. Do you understand what I'm saying? No, it's weird.
Velocities don't have.
Oh, this is where
Yeah.
the 10 feet.
It's not where the 10 feet. So that's a good question, though, Alexa. I didn't bring this up.
Why did you
The
say
10 feet doesn't matter.
God.
I know, it's so
Oh, that's
frustrating
so
for
frustrating.
students. So, does it matter in real life? Yeah, it probably matters if she's 10 feet from the light or if she's like 3 miles from the light, right? What if the light was as powerful as the sun, though?
She would be dead.
Yeah, because it's really close. Yeah, but if that light was like, could go through and not have any of that like light wave crap, like everything's in the air is messing it up, diffusing, I don't know, what is the word for that? You guys are in physics right now. The light is being scattered, right? The further she's away, like clearly, if she's 3 miles away, you're probably not going to see a shadow from that light, right? But if that light is super powerful, you would still. It doesn't matter how far she is from the light. I know. If you're on the other side of the world, if it's a straight line, ugh, you're driving me nuts. All right, so anyway, so we don't ever use that 10 feet. It doesn't matter how far she is from the light. There was no place to even plug that in, right? It doesn't matter to mess with you. I put it in to mess with you. All right, so the question is, how fast is the tip of her shadow changing? So the tip of the shadow involves both the distance that you are from the light and the length of the shadow, right? So we're talking about where is this right here located? It's located x plus s away.
So you have to find x.
So we find the derivative of both. Dx over dt plus ds over dt is the rate at which the tip of the shadow is moving.
Okay, so you found. Oh.
So that's for part B. So you take your 4 that you had from before and you add it to the 2.316 and you get 6.316. So the AP test could ask either. I know it's frustrating. You took the original velocity, how quickly she was walking away, and you added it to the rate that the shadow was changing at that point.
What's x for again?
X was the distance that she is from the light. So see the picture?
Oh, it was the sun then.
It's not the sun. I'm saying if that light was as powerful as the sun. All right, so now here's the next one. So this is, all you physics people are not going to like this one either. All right, so number 2. So a sandbag is dropped from a balloon at a height of 60 meters when the angle of elevation to the sun is 30 degrees. Okay, that 30 degrees is a fixed angle. Okay, here's the situation that's happening here. Here's the sun. Here's Earth. When the sun's rays come down, you basically create parallel rays. So you know how, like, if you stand, I have to explain this to my geometry students all the time as well. So I always draw the sun like this. That's not what the sun looks like. The sun is freaking huge if it's that far away in comparison to the, right, does it make sense? The sun is massive. So it's coming down and you're creating a shadow. Well, a person also has the same degrees here, the same one. I could draw the person on this side of the tree. The shadow for that person is not like that. Okay, these are parallel rays that are created. Okay, so it's like this. So here's where the person is. The sun is still coming down like this.
Like theoretically, the angle is a little bit smaller.
Yeah, we're on the other side of the tree.
All right. I mean, it doesn't matter where in location to the tree. You are in this.
But the tree
You're-
would cast a shadow.
Whatever. Okay. So we have parallel rays coming down from the sun. Shh, guys. So these parallel rays at this time of day are 30 degrees. Okay, that's the fixed point. And as this drops, we're creating a shadow. So do you guys see the little shadow of the sandbag? It was on that picture. What happens to the shadow as it drops?
It's closer.
It gets closer. It goes really fast. Do you guys understand this? So as this drops down, what happens is this shadow shoots over really fast, directly underneath it. Does that make sense? I should have like an experiment where you take a video of something like this, you dropping something, and you can watch it. But basically, the shadow goes directly underneath it until there's like no shadow because it's directly underneath it, right?
Well, it's at 30 degrees, so there's gonna be.
Right. Well, if it's 30 degrees and there's no triangle created, then no, there's nothing there. All right, so here we go. So we're going to do this problem, and we're going to have the length of the shadow, so I'll call that x. And this one I'm calling, I don't want to call it s because it's the height, but I'm going to call it s because that is the position function that's written there. 60 minus 4.9 t squared. Okay, that has to do with gravity and so on. We'll talk a lot about those. We have talked a little bit about those, right? If gravity is negative 9.8, then when you take the antiderivative. Right? So you have acceleration, then you have velocity, then you have position. Right, so we want to create an equation. So our equation is tangent. So it's tangent of 30 degrees equals opposite, which is s, over adjacent, which is x. I don't want to write it as s, though. I'm going to go ahead and plug in 60 minus 4.9 t squared.
You can plug it in already.
Yeah, you could do the s, too, if you want. It doesn't matter. I'm going to multiply the x over, so I get x times tangent of 30 equals 60 minus 4.9 t squared. This just makes it easier for me to take a derivative. Do you guys know what the tangent of 30 is? Yeah, you should know it. I agree with that statement. We should know it.
How would I know?
It's 1 over root 3. It's the sine over the cosine, right? 1 over 2 divided by root 3 over 2. So it ends up being 1 over root 3. So we have 1 over root 3x equals 60 minus 4.9 t squared. So when we take the derivative, I get 1 over root 3 dx over dt equals negative 9.8 t. And then I get dt over dt. Are these t's the same units? They are. It's time. I'm just tricking you. It's time. So the derivative of time with respect to time is just,
Time.
it's 1. dt over dt is 1.
What?
That makes me mad.
It's like change in y over change in y. Right?
Oh
That's the
my
same thing.
god. So if you ever have
Alright.
anything with time,
What happened to the 6?
time's always changing, so it's just one.
It's, yeah, it's 1.
Time divided by
What do you
Oh,
got?
never mind. Time
If
gone
you find
crazy.
time,
We
I
took
feel
the derivative.
Okay, so we took the derivative, and now we're going to plug in, what do we know? So we're trying to find when the height is 35 meters. Okay, I don't have height or s or anything in here. I had changed it all to t, right? How do I find t if I know the height is 35?
Well, we solved that equation.
What equation? 35 is equal to what?
The equation of
60
the
minus
drop.
60 minus 4.9 t squared. So do that. So use your calculator, find that number. So I get t equals, I'm going to take the square root of the 5.1 number. Did you guys all get the 5.1 number? So I get 2.2587 something. Okay, I'm going to take that number and I'm going to replace t with it. So I get negative 9.8 times my answer. And then how do I get the dx over dt by itself? I multiply by root 3. So I get negative 38.341, and this is in meters per second. Think about what this means. Is the distance x, is it getting smaller or bigger? Smaller. Is that what we thought in this situation? We talked about the shadow moving and zipping directly underneath the back. Right. That's totally what's happening. So our distance is getting smaller there. So how would you write a sentence on the AP exam? Because it will often say, explain using units.
You could say that it's changing at a negative rate, or you could say
Exactly. Changing at a negative rate or decreasing at a positive rate. Can't say decreasing at a negative rate because we don't do double negatives in math, right? You guys remember that? Okay, so that's our answer. All right, any questions on any of that now? So Phil, do you still have your question? He's not paying attention. Do you know what it was? Did I answer it?
It was for the last problem. I was just
Oh.
confused on height and length.
The height and length on why it was H and L?
Yeah.
Well, I didn't want to have two H's, so I made one of them L, so I wasn't confused. Yeah, L is 5 anyway, yeah. So do you want me to write equals L here? Will that make it nicer? All right. So let's stop there.